Hello, welcome to this video. This is 7-4 and we are talking logarithmic functions. We'll also talk expressions and equations in 7-4, and really this video lesson, well, I'm going to split it into two, but these video lessons are going to recap what you learned about in Accelerated Math 3 or pre-calculus about logarithmic functions, logarithmic equations, and just general properties of equalities. Okay, so this is a lot of content, so I'm going to kind of break it down. I'm going to go slower and try to be as clear as possible, but if you want, please feel free to revisit what you learned in Accelerated Math 3. I think by the time you view this video, I'll have gone in and made a whole series of videos on logarithms for my Accelerated Math 3 class, so hopefully you can go back and view that if you want. But hopefully a lot of this is review. So not saying that you've mastered it or that it's fresh in your mind, but okay, just know that a lot of this content is going to be review. All right, so without further ado, let's go ahead and talk about logarithmic functions and kind of where they come from. Now, the foundation of logarithms, okay, which is an inverse to our exponential functions, starts off with our understanding of e to the x, or just an exponential function. So here we have f of x equals e to the x, and that is this graph here. Okay, so if I wanted to find the inverse of this function, I could go ahead and switch x and y, and I would end up with this equation. Y is equal to e to the x, and I would end up with x is equal to e to the y. Now, with algebra, I can't bring down a power. I don't have the algebraic tools to do that. So this is where logarithms comes from, okay? And again, logarithms are derived from the inverse of an exponential. Okay, so how do I find the inverse? Well, I'm going to switch x and y. So if I switch all of my x and y ordered pairs, I end up with this graph here, which is, in this case, log base e. This is log base e of x, okay? And log base e is commonly known as the natural log of x. So there you have it. That's what a logarithm is. It's the inverse of an exponential. Now, I want to highlight two different and very important kind of logarithms that we'll use frequently. We have log base e, which is known as the natural log of x. Again, this is the inverse of e to the x. Okay, and then we'll also encounter log x. Okay, which is known as log base 10 of x. So you'll notice that commonly these bases go away, but just know ln of x is the natural log of x, and then log base 10 of x is log x. Okay, so before we talk about the graphs, I want to go ahead and I want to talk about example 1. It says use a calculator to graph y equals the natural log of x and y equals log of x in the coordinate plane. So I'm going to pull up our calculator, our graphing calculator. We'll add some graphs and we'll plot these in. So the first one we'll put in is the natural log of x. There is the natural log of x. And we'll go ahead and put in log base 10 of x. Okay, so with the TIs, we're lucky we can enter bases. Some calculators that you work with, they won't have the option to input the base, but here we're lucky I have log base 10 of x, and there are the two functions, okay? And you'll notice in your notes, example 1 says, what do you notice? Like, what do they have in common? And the main things that you should notice is that we have a vertical asymptote on the y-axis, x equals 0, and we have an intercept here at 1, 0. Okay, so I'm going to go ahead, come over here, and I'm going to plot these. So y equals the natural log of x. I don't know why that keeps disappearing. Wow, magic. It does not. Dude. There we go. Okay. Glitches, magic. Y equals natural log of x. So they both have intercepts at 1, 0. Okay, and this one go a little bit like this. Okay, and y equals log of x, again an intercept here, and then this one is more tight. If you notice, if you look at the graphs, I flipped my colors, but the log base 10 right, is closer, it's more compressed to the x-axis. Okay, and that looks something like this. Whoa. Okay. That's bad. I can't stand for that here. Oh, man. There we go. Okay. So there's our two functions, and again, the similarities, you should notice the asymptote and the intercept. So with that, we'll go ahead and we'll talk about the properties of logarithmic functions. Here it says if f of x equals log base a of x and a is greater than 1, then the domain is from 0 to infinity, and notice that's because of our asymptote. Our range is all real values, negative infinity to positive infinity. And this should make sense because this is the inverse of an exponential. Remember, an exponential had negative infinity to positive infinity, and then the range was limited. Well, here, it's switched, and that makes sense. The graph is continuous. It's increasing and concave downward. Okay, and again, we have a vertical asymptote, and we have a key point, which is an intercept. The other key point, and maybe you'll notice when I started plotting these, is I put down a secondary point. So I put down at 2.718, comma 1, which maybe actually my graph's a little bit low, maybe about here, and then 10, comma 1. Actually, no, I was right. Control Z. 10, comma 1 over here. Sorry, 2.718, comma 1. Yep, right there, and then 10, comma 1 right here. So those are just kind of the key characteristics of a graph. Now I'm going to go ahead and I am going to look at example 2. So example 2, it says without using a calculator, sketch the graph of y equals the absolute value of natural log of x minus 2 and write an equation for the graph's asymptote. So looking at this graph, we have a h value of 2, so we're going to shift to the right 2. Well, that means I'm going to have an asymptote at 2. Okay, and that would mean that then I would have an intercept 1 over. Okay, and my graph would look something like this. Now it's natural log, so that's base e, right? Natural log of x is log base e. So 2.7 over, so 1, 2.7 up, and then up 1. I'm going to have a point roughly about here. So there's my graph, except for the fact, right, that I have an absolute value. So when I have an absolute value, again, everything that's negative is going to go away, and it's going to become positive. So it's going to look like this. Okay, so there is our graph. All right, now the next thing that I'm going to talk about is how do we go from a logarithm to an exponential, or an exponential to a logarithm. Okay, and this is kind of our change of form definition, or kind of the pattern. And again, this is review. We talked about this in Math 1, and what I want you to notice is I'm going to point out the similarities in the base. So here for this logarithm, y equals log base a of x. Notice that the base is a, and then over here, what's the base? A for my exponential. Okay, so that doesn't change. And again, logarithms and exponentials, they're inverses. So inputs and outputs switch. Okay, so this should make sense. Well, notice over here for our logarithm, I have an input, okay, which is x. And then notice that it becomes over here what? It becomes the output. All right, well, that makes sense because they're inverses. And then vice versa, right? Now I'll use another color. So over here, I have the output. Oh, no. Hey, Ella. Hi. Hi. And then over here, I have it's the input, okay? So that should make sense, right? They switch. So here, example 3, it says, change the following equations from exponential form to logarithmic form, or vice versa. Well, I have an exponential, okay, and notice the base is 3. So it's going to be log base 3, okay, and then the input and the output switch. So it's going to be log base 3 of 81 of, and sometimes you'll see parentheses, sometimes not. If you have a more complicated, what we call argument, or your input, then you'll see parentheses, and this is equal to the output, which is 4. Okay, over here, base e. Well, I have log base e, okay, input and output switch. So 1, which is equal to 0. And again, this is a rookie move. Log base e, that's known as what? Natural log of 1, okay, is equal to 0. All right, good. Over here, log of 0.1 is equal to -1. Well, what's the base? It's invisible. Well, when it's invisible, it is base 10. So 10 to the power of -1. Again, input or output becomes input, and then the input becomes the output. This is equal to 0.1. All right, so that's just switching inputs and outputs, okay? And then here, example 4, kind of the same ideas, but these are really touching amongst properties that you should know. It says, since e to the power of 0 is equal to 1, then the natural log of 1 is equal to, well, 0. Again, inputs and outputs switch. Over here, if e to the power of 1 is equal to e, then the natural log of e is equal to 1, right? I mean, these are kind of fairly common, right? All right, so because the natural exponential functions and natural logarithmic functions are inverses, then the natural log of e to the power of n and e to the power of natural log of n is equal to n. These are inverses. They don't cancel out, but they essentially cancel out. We can think of it that way, right? They undo each other. All right. So over here, it says, use the inverse idea from example 4c to simplify. So if I have the natural log of e raised to the power of root 2, well, those are inverses, so our answer is just root 2. Here I have e raised to the power of natural log of 3x. Well, those are inverses, so we get 3x. Over here, I have 10 raised to the power of log of 2. Are those inverses? Well, what's the base on that log? This is log base 10. So they're inverses, so they cancel, okay? And then here, log base 2 of 2 to the power of x squared. Well, again, log base 2 of 2, inverses, they cancel each other out. All right, okay. All right. Okay. Next up, I just want to do 2 more examples in this video here, is talking about properties of logarithms. Now, we have some fairly common properties, and the first one is dealing with products. If your argument is a product, you can expand it out to be the same logarithm, same base logarithm. In this case, natural log of a times b is equal to the natural log of a plus the natural log of b. Now, since this works for multiplication, it also works for division, but instead of adding, we subtract. So the natural log of a divided by b is the natural log of a minus the natural log of b. Okay, so those are the 2 most common that you'll use to compress and simplify natural or just logarithmic expressions. And then the other one that's used is the power property of logarithms, where if I have an argument with a power, I can bring down that power out front. Okay, so the natural log of a to the power of n is equal to n to the power times natural log of a. Okay, and that works for any types of base. So let's go ahead and check this out. Number 6, it says expand using logarithmic properties 1 through 3 above. Okay, well, natural log of 5 over 8 is going to be, well, I'm using property 2. This is going to be the natural log of 5 minus the natural log of 8. Simple. Here, I have the natural log of the cubic root of x squared plus 1. Well, I'm going to go ahead and rewrite this as the natural log of x squared plus 1 to the power of 1/3. And notice, right, I have a power. I can go ahead and bring it down out front. So I have 1/3 times the natural log of x squared plus 1. Now, can I expand this logarithm here? Well, the answer is no, because they are adding, not multiplying or dividing. Okay, so make sure you're aware there. And then example 7, which will this will be the last example in this video, it says condense these into a single logarithm. So instead of expanding, we're going backwards. So you kind of need to reverse your kind of train of thought here. So A, -3 natural log of x plus 5 natural log of y. Well, I'm going to use the power rule here first. So this is the natural log of x to the -3rd plus natural log of y to the 5th. Okay, So since I'm adding these logarithms and they're the same base, I can go ahead and multiply them. So I have natural log of x to the negative third times y to the fifth. Okay. And then part B, again, I'm going to use the power property first. So I have coefficients out front. We'll go ahead and make this the natural log of x to the power of 1/2 plus the natural log of x plus 1 minus the natural log of y to the third. Okay, so now notice I have everything that's the same base. Log base e. I'm going to go ahead and simplify the first two. So I have the natural log of x to the power of 1/2 times x plus 1. Okay, minus the natural log of y cubed. All right, well, since I'm subtracting the same logarithm, I can go ahead and divide the arguments. So I have the natural log of x to the power of 1/2 times x plus 1 divided by y cubed. Okay. All right, so that is it for this video. We talked about logarithmic functions and logarithmic expressions. Again, there's a lot, I know. There's going to be a second video talking about equations where we're going to solve, okay? So if you need to, watch it again, pause it, even try some example problems in your problem set to see maybe do I have the hang of it, okay? And I'll catch you next time. Peace.